All right, so it's 8:50 and we can get started. Welcome to the 6th Internship Symposium of iDASH. It's a pleasure to have you all here, as well as those who are attending online. Here's some instructions of those attending online. We are also recording this for future viewing. And I must say, first of all, I want to thank the organizers for having this all done. As you know, there's a lot of logistics involved in creating the appointments, getting everyone on board, and then organizing this presentation. So as you may know, iDASH is a project that has been going on for a while, since 2010, and it's a National Center for Biomedical Computing funded by the NIH. We have several goals in the National Center, and this circle just shows some of the items involved in biomedical informatics and how some of the specialties are distributed. And you all worked in one of those boxes here, but I want you all to know that there's much more to biomedical informatics than what you could see in about 10 weeks of your internship. So our goals with the iDASH are to share access to data and computation, to train the next generation of data scientists, and provide innovative software platform and infrastructure in order to accomplish that. We, most of all, want to protect the privacy of our patients, of our institutions, of our providers, and develop algorithms, tools, infrastructure, and policies to allow data sharing without compromising the privacy of anyone. We have a lot of partner projects. These were some of the last ones, and they resulted in papers that are coming out right now with, for example, consent for data and biosample sharing in underserved populations is a project with Arizona Maricopa Health System, and it's just coming up in the Journal of the National Cancer Institute. And we also have other projects related to informed consent, and that's when the patient could select which items they want to share for research, and then we can control that from our clinical data warehouse. Some of you have been involved in distributed computing algorithms, and that is when we have institutions hold on to the data but allow computation on that data. So that allows full control of the institution of what they allow access to for what purposes, and this has been a big focus of our work. More recently, we've been involved in the Data Discovery Index Consortium, and that is about to do for data what PubMed did for the literature. And PubMed, as you know, is a public source of information, of articles in the biomedical literature. So we could do the same for data. That would be of great value, and we are just starting to go that route by indexing data sets and making them discoverable. So there's a project going on about that involves getting repositories, data sets, and having data producers format the data according to standards that then can be ingested and manipulated so that data searches across the internet can be facilitated. Another work that we do is on clinical data research networks, and we happen to lead a very large one composed of all the University of California medical centers. That's about 13, 14 million individuals. It also has the VA Enterprise Data Warehouse. That's all the VAs in the country, all states and territories. That is actually a little bit above 11 million. And also our colleagues in LA and Colorado, Washington, and other parts of the country. So a lot of practical hands-on possibilities for those who are interested in data sharing in a privacy-preserving manner. So today we accomplished item 1, which is take the group photo. And as I said, those who missed it, please be available so that we can Photoshop you in the picture. And we'll have a very full agenda today, and we'll be paying attention to the clock very closely, and that's part of training, getting your presentation finished on time. So we will start with Breast Cancer Trajectory Explorer, and then Stress Monitoring Project, Improving Mental Wellness through Expressive Arts Therapy-Based Social Support, and Complementary Integrative Therapy Evidence Detective. That's intriguing. And the PCOG project. Then we'll have a little break, very short as you can tell. We'll go through privacy-preserving patient linkage based on secure multi-party computation, privacy-preserving genome data analysis using SGX, implementation of genomic data into UCSD's clinical data warehouse for research, distributed learning from multiple electronic health records databases, contextual embedding models for medical events, and finally, designing a community-based chronic disease self-management program with an informatics strategy. And as you can tell, our interns this year come from a lot of places. These are their portraits here, but more specifically where they come from is in the map. So you can see the diversity of institutions, and we're very fortunate to have you here after a very selective process with a lot of applications. We also, not portrayed here, have 4 high school students who have joined very recently and who will be working with us the rest of the summer, and hopefully longer term as well. In terms of the past, between 2011, which was our first year, and last year, we have hosted more than 70 students from 30 institutions, which include 1 high school, 20 undergraduates, 20 masters, and 30 PhD or MD students. So there's a lot of people we still have to add this year's one. The number of interns that we were able to accommodate every year depended on the funding, and here's an average, so about 13 every year, so that's very exciting, and we hope to continue for future years. Every year the activities change a little bit, and we stick to the ones that were most popular in terms of recreational and getting to know San Diego area. So this was pictures from last year. In Shelton at the end we'll show some pictures from this year. So without further delay, because the talk has to start at 9, I would like to invite our first speakers to come and remind them to talk on the microphone, because we are recording and we want you to show to everyone, put on your Facebooks and other social networks afterwards. So please welcome our first speaker.
Hi everyone and good morning. My name is Mira Reganathan and this is Elizabeth Epstein. We're both medical students at UCSD, and this summer we've been working on a breast cancer decision aid called the Breast Cancer Trajectory Explorer. We've been working with an amazing team of people who've been really inspiring and really taught us so much, so we're just really lucky to have them. So our agenda for our presentation is to start with the statement of the problem, talk about the gap in knowledge that we're trying to fill. Then we're going to talk about the proposed solution, which is our Breast Cancer Trajectory Explorer. And then we're going to talk about our design process, which is the specifics of how we plan to optimize our design to make it the most useful it can be for breast cancer patients. So to start with the statement of the problem, the really cool thing about breast cancer treatment is that decision-making is really patient-driven. We imagine patients to be going along a trajectory of treatment. Usually right after diagnosis, patients undergo some sort of surgery, take out as much of the tumor as they can, And then they undergo radiation and chemo, and finally end with some sort of medication for long term. The thing about these therapies is that there's so many options. There's a whole menu of surgeries that a patient can choose from based on their personal beliefs on body image and breast conservation, etc. So for radiation and chemo, there's a decision whether or not to do those, because with all cancer therapies, there's a lot of pretty severe side effects that have to be considered for a breast cancer patient. So when we imagine what a breast cancer patient has to face upon diagnosis, we kind of visualize it as a giant web of decisions. For surgery, there's many, many options, and then it just branches and branches. And if you can imagine, for a breast cancer patient, this can be pretty overwhelming. So just zooming in on a small part of this network, just a small part of radiation, chemo, and medication is so complex, and patients have to face even more than this. So our goal is to be able to place patients on this web and help them find the thread of decisions that works the best for them. So patients day in and day out are making these life-changing decisions, whether to have chemo, what kind of surgery to get. And so the question is, how are they making these decisions right now? So we try to think of breast cancer patients as kind of using 3 buckets of information. There's the data from clinicians, which breast cancer patients are going to see the whole array of doctors. They're going to see primary care physicians, oncologists, radiation oncologists, surgeons, and these are all giving them their own information. Then there's going to be the study data, which is, as a lot of patients do, they're going to search the web and be exposed to all these research articles and also get data from those studies. And then finally, and most importantly, is the anecdotal data. So breast cancer is the most commonly diagnosed cancer amongst women. So there's like a huge, huge network of women that exist that are constantly talking to each other, sharing personal experiences. And past literature has shown that this exchange of anecdotal data is actually the most influential in patient decision making. So this really interests us because we have to figure out how we plan on presenting this data to breast cancer patients, the anecdotal subjective data. Also on the side, we have these decision aids. We didn't put it in with the other sources of data because research has shown that current decision aids aren't playing a huge role in patient decision making. When we say decision aids, we're talking about the pamphlets and maybe some online tools that exist to help patients make their decisions. But it seems like right now, patients are more drawing from those 3 main sources of data rather than the existing decision aids. So specifically, study data is from journal, websites, books, and pamphlets. Data from clinicians is from the whole array of clinicians, from surgeon to even genetic counselor. And then anecdotal data is from family, friends, support groups, and online health communities. The first thing that should strike you is that this is so much information coming at breast cancer patients. It's just coming from all directions, and even at home there's the internet, which is always ready to give more information to the panicked mind. But this is coming from all different sorts of directions, and a lot of it will be conflicting. So it's really disorganized. Also, we were specifically interested in these online health communities because we wanted to see how is this subjective, one-on-one personal experience being exchanged, what kind of information is being shared and received on online health communities, and how might that influence how we make our tool. So this summer, one of our sort of sub-projects was looking at online health communities. And so we specifically decided to look at WebMD. And we looked at the first post of all the posters on this forum to see what's drawing people to these forums. What is the question that's plaguing them, that's making them post on the forum. So we looked at all these posts, and what's interesting is that both patients and caregivers are posting on these forums. So it's not just the breast cancer patient, it'll be the partner or the sister or the daughter that's also seeking something from these forums. So we analyzed demographics of the poster, the content, and the themes of the post. And what we found was that caregivers seem to be going onto the forums to be seeking emotional support while patients were going on the forums to seek information. When we just analyzed what patients were doing with their first posts, we found that the most frequently conversed topic was chemotherapy, followed by radiation, and then medication, then surgery, and then reconstruction. So doing this analysis gave us insight as to what patients are talking about and what their questions are about, which was really interesting. So looking at existing data, we are zooming back out. We just looked at the online health communities, which are specifically anecdotal. And then we want to look at what are the limitations of all these existing data so that we can overcome these limitations with our tool. So it seems like study data kind of has a lack of granularity. It's not really applicable to the patient as an individual, because usually study data is about groups of patients with similar aspects, but it doesn't answer those patient-specific questions. Then data from clinicians lacks that subjective experience. You know, doctors have a lot of good information to share, but since doctors haven't been through the same experiences that patients have been through, there's that lack of, the human level, the shared experience, which is making that data exchange more difficult. Then with anecdotal data, it's really great that patients can connect on a human level, like, oh, we both have kids, or we both go to the same church group. But because of that, patients might not understand how different their disease is from another patient. So that makes that data not as valuable in the settings that it's being presented in now. So when we also looked at current decision aids, because we are trying to make a decision aid that's better than the ones that are currently available, we found that they're limited in scope. They usually only address like one treatment, like just surgical decision making or just chemotherapy decision making, rather than following the patient along their whole treatment trajectory. They are not frequently updated with like the most recent literature, because breast cancer research is constantly ongoing. There's so many new and amazing things being discovered, but these decision aids aren't being updated with that information. And also, it seems like the decision aids aren't incorporating the subjective experience that we found in those online health communities was so important and so influential in patient decision making.
So now I'm going to talk to you about our proposed solution to address those limitations that Mira just talked to you about. And that is the Trajectory Explorer. It's a web-based decision aid for breast cancer patients that is really meant to integrate all of that information and help them organize the information throughout the entire course of treatment. So Mira talked to you about those limitations, and our decision aid overcomes those limitations. So it covers all treatment modalities, and it assists the patient throughout the entire course of treatment. It also includes the latest literature, also is informed by consultations with breast cancer clinicians, and also real-time user feedback from the application. And maybe most importantly, it provides experiences of other patients who have selected those treatments, so they get that subjective data as well. So now I want to introduce to you two patients who we imagine might be using the application. So first we have kind of a typical patient. Jennifer is 49. She was diagnosed with breast cancer 2 weeks ago. She's really considering all surgical options at this time. Kind of everything's on the table, and she really just wants as much information as she can get. Another factor that's important to her is that her current cup size is a double D, so she will want at least some reconstruction to feel balanced. So that's something she's also going to want to get information about. And her oncologist says that chemo and radiation are inevitable, so she wants to get information about those inevitable treatments down the line as well. And now Amanda has kind of a rare situation. She's 47, she's a mother, so that's something she might want to connect with other patients about. And she was just diagnosed with early stage breast cancer. But she had Hodgkin's lymphoma 10 years ago, and she was treated with chest wall radiation. So that's going to be something that puts a limitation on the treatment she can receive for her breast cancer now. And she's leaning towards bilateral mastectomy with latissimus reconstruction. So she just kind of wants to get reassurance about that option and hear from other patients who are like her, even though she has a rare situation. And she's worried about her cancer recurring. So now I'm going to talk to you about the unique features of the Trajectory Explorer, which are all working together to really meaningfully engage the patient in the decision-making process and ultimately facilitate organization throughout the entire process. So all this data that Mira talked to you about, organizing that data so the patient can make as much of an informed decision as possible with the least stress as possible. So first, our application incorporates 3 distinct data sources. So all those types of data that the patients are using to make decisions that Mira talked to you about, we're including that data in the application by using data from large studies first. So that has the benefit of having large numbers of patients with long follow-ups. So they can get information like risk of recurrence or chance of survival. And we also have more granular data from the UCSD Clinical Data Warehouse, which allows patients to get some more specific questions answered, like what are the chances I'll be able to complete this course of medication, or what are the chances I will have to have another surgery after having lumpectomy. And finally, we have data from online health communities. So we're organizing 320,000 posts. We've completed analysis of 8,000 posts at this time. And that will really give qualitative data to patients and organize that data so they can have a real clear view of what other patients are saying about these treatments. So we're really just organizing and integrating all this data for the patients to use the application. So here you can see what a patient would see with different data sources for different treatment options. So these are 3 different types of surgery, and you can see personal survival probabilities, risk of local recurrence, and then also you can see what people are saying. So you get that subjective data as well. The app also has a user profile, which is really the central hub of the app, where the patient enters information about them, like their BRCA status, their pathology, and the app then is able to give them information that's specific to them. So they're only getting the information that directly applies to them. They can continue to update that information throughout their disease treatment. They also have customized information displays, which allows them to not only get data that's specific to them, but the data that's of interest to them. So if they want all 3 types of data and that's important to them, then they can have all 3 types of data in an organized way. But if they really just want to focus on data from the national studies, they can just have that type of data. And it's a web-based mobile application, and that means that they can access the application on both a mobile device or a computer, so whatever is most convenient for them. And they're able to take the application with them and take notes using the annotation mode. So that allows for them to store additional information from additional data sources like their clinician. And another interesting feature is that it helps them to find the questions they need to ask and figure out, and it suggests to them what type of clinician they should direct questions at, which can be a difficult thing for patients to figure out since they're seeing so many different types of clinicians. So they can then take notes on those questions.
Okay, so now we're going to talk to you a little bit about the design process of how we plan to optimize our design and make it really useful and usable for breast cancer patients. So just as an overview, we first plan on extracting our design requirements to figure out what we really need to put as the focus and main design of our Breast Cancer Trajectory Explorer. Then we plan on building prototypes and iteratively optimizing them until we come up with a final really good, robust prototype. And then we plan on building the full-fledged Trajectory Explorer and evaluating it with real breast cancer patients to make sure that it's usable and navigatable and is really helping out with decision making. The cool feature is that every single step of our process is optimized and informed by user feedback with real breast cancer patients. So the first thing we have to do is figure out our design requirements. So we're going to do that with in-depth qualitative interviews with breast cancer patients. We want to figure out what are they struggling with in their decision-making process. What do they feel like they don't know enough about? What do they know too much about? And we want to figure out how they like to receive information so that when they're using the application, it's easy to use and they're getting the information that they want. Then we're going to consult with breast cancer clinicians and also get their feedback as well. And then finally, we're going to formulate our design requirements so that we can build our first prototype. We're going to build those prototypes, and we're going to present them to the breast cancer patients in interviews. We're going to gain their feedback about those and just continue to improve our design until we end up with a really good, high-fidelity prototype. Finally, we're going to evaluate our Trajectory Explorer in many different phases, ending in a very large study with breast cancer patients that's multi-institutional and single-blind. We're going to give the experimental group the Trajectory Explorer to use, and we're going to give the control a traditional decision aid. And our goal is to reduce their decisional conflict. So our goal is to make sure that they are able to make the decision, feel confident about it, and feel like they really knew all their options. We're going to measure this. We're going to measure our success through various different scales, the most important of which is O'Connor's Decisional Conflict Scale. This is a scale that basically asks questions like, how certain are you of your decision? Do you feel like you know all your options, etc.? And it's a 16-question questionnaire. And we're also going to accompany that with qualitative interviews, feedback surveys, and quality of life surveys. And our goal is that after use of the Trajectory Explorer, their decisional conflict is going to go way down. They're going to feel like they know all their options. They're going to choose one with confidence and certainty, which is our goal for any patient who's undergoing cancer therapy.
So now let's check in with our patients. And these patients were derived from real posts that we analyzed. So we're kind of imagining how the decision aid may have helped them throughout their treatment process. So if we remember, Jennifer was kind of our typical patient. She was looking at all surgical options, and she really values the subjective experience. So she enjoyed using the application to see what others were saying about her disease and gain a really clear view of what others were saying about different treatment options. She also got ideas of questions to ask her doctor and was able to take notes in the app. And she was ultimately able to choose lumpectomy with radiation. And we'd imagine that when she took the DCS that Mira was talking to you about, she scored low, meaning that she was very happy and confident with her decision. And we also imagine that she was able to continue using the app later down the line when she was deciding whether to take a SERM, which is a type of medication that's available to breast cancer patients. And Amanda, so she had, despite her rare situation, she was able to use the application to hear from others in the similar situations because it includes so much data. She was able to hear from people that were like her. And she was also able to relate to others' concerns regarding being a mother. And she was able to confidently choose bilateral mastectomy, which we also imagine she scored low on the DCS, meaning she was happy with that decision. So just in summary, we stated the problem, which was that breast cancer patients need consolidated treatment information. They need a way to organize all these different types of data so that they can make the best decisions possible. And we talked about our proposed solution, which is the Trajectory Explorer, a web-based mobile application that takes these different types of data and organizes it for them in one place and provides it to them in a way that's specific to them. And we talked about our design process, which is optimized by user feedback, which is very important because it allows us to create something that really will be useful to patients and evaluated by the DCS that Mira talked about. And in the future, very soon, we're going to begin patient interviews, and we're going to begin analysis of the UCSD clinical data warehouse data, and we're going to continue analyzing data from online health communities. We really want to thank our mentors, our amazing mentors, Dr. He and Dr. Marmor, and all of our collaborators. It's seriously so humbling and incredible to be able to work with them. They're amazing. And everyone else we work with, all the professors and staff, interns, iDASH, DBMI, NIH, and the UCSD Summer Training Grant, which allows us to work this summer. Thanks so much, and we're open to any questions now. Yes. I think we're planning on doing about 30 interviews in total for those. And we're going to do those until we stop receiving valuable feedback from them.
For the second presentation, and the topic is stress monitoring project. All right. Hi, everyone. My name is Ted, and this summer I've been working on the ID Stress project, which stands for Individualized Detection and Evaluation of Stress. My project mentor for this project was Hyunhee Kim, and for a bit of background information on myself, I recently graduated from UC San Diego with a major in computer science. So as you might know, caring for patients is inherently a physically and mentally challenging task. There's currently a shortage of healthcare workers, and because of this, they're working very long shifts that can range up to 12 hours. On top of that, there have been increasing numbers of reports of problems working with patients. For example, patients might be uncooperative, and their families may be inconsiderate towards the workers, and even coworkers can be uncooperative at times as well. So with these things put together, it can lead to fatigue and even burnout for these healthcare providers, which overall leads to a diminished quality of care. So what can we do to solve this problem? How can we reduce stress with these healthcare providers? We had the idea of creating a stress management application for these nurses. This application would make use of a commercial sensor device that would automatically monitor the nurse's stress level, and it also alert the nurse when their stress levels reach a certain threshold. And it could then provide a suggestion to relieve that stress. So we think that this application could benefit the users on a personal level, but we can take this one step further as well. We think that our application can benefit groups by allowing for group stress management. This application can store data online for visualization, and it can also calculate a team average stress level. Using these average stress levels and showing all the other data can allow supervisors or team leaders to recognize patterns of stress throughout the day that they might want to address. Also, we want to make sure that the data remains private and anonymous so that we can maintain user confidentiality. So throughout my internship, we were studying whether or not this application was feasible. We wanted to ask the questions, does an appropriate sensor exist? Can we use the data to actually calculate a stress level? Is there a good way to present this data? And can we protect the user's privacy in doing so? So after doing some research in wearable sensors, we determined that the Microsoft Band 2 was the ideal candidate for this project. The Microsoft Band 2 can track important signals such as the heart rate and galvanic skin response, which are important signals for tracking stress levels. It's also compatible with Android, iOS, and Windows phones, which covers the majority of smartphone users. So now that we have a wearable sensor, we can lay out the data flow for our project. First, the nurse puts on the wearable sensor, and then they connect that sensor to a mobile application via Bluetooth. And then from there, the mobile application periodically uploads data to an online database, where we then push the data to a web application. So this is a sample screen of the actual mobile application that we've been developing. The purpose of this application is to act as a gateway between the user and the online database and the web application. On the left-hand side, you can see that there are checkboxes next to each signal that we're trying to track. This makes sure that the user is able to provide consent before we actually start tracking and recording their data. Once they check the boxes and give that consent, the values that they are recording shows up on the right-hand side of the screen, and the data is stored in the database. Another feature of our mobile application is the threshold page. This page allows the user to set a certain threshold for themselves so that the application can notify them when they become stressed out to a certain point. This threshold ranges from a minimum of 0 to maximum of 100, 0 being the lowest level of stress that they have ever recorded, and the max being the highest level of stress that they've ever recorded. A third function of our mobile application is the logging functionality. This allows users to record what they're doing throughout the day so that they can later go to the web application and view their charts and see if they can recognize any patterns with their stress according to things that they did that day. That way they can see if certain activities cause them to be more stressed out, and they can perhaps avoid those activities in future or consider trying to be less stressed out as they perform those activities. So this is a sample of the actual web dashboard that we've been working on. This dashboard presents the data that the users have recorded on a chart that they can review, and they can also scroll through the graph and find certain times of the day where they recorded higher stress levels. They can also select log entries that they recorded on their mobile application to quickly navigate to that point in the chart. So another feature of our web dashboard is the group signals page. This allows users to compare their own signals to those of their group, as well as an average of the total group. We think that supervisors and team leaders might be able to use this page to address certain problems. For example, at the top you can see there's a red line that represents a nurse who's had a higher stress level throughout the entire day than the rest of their team. So a supervisor might be able to see that and talk to that nurse and ask if there's anything they can do to help relieve that stress. However, we also understand that there are some issues with privacy with a chart like this. So we've been working on adding different levels of permissions and access levels so that the user's data is private and confidential. You might be wondering how we actually calculate the stress using this data. Our algorithm is currently a work in progress. We've been working on calculating the stress in 10-minute intervals. So first, we get all the data in a 10-minute interval, and we find the mean and standard deviations of that data. And then we compare those means and standard deviations to a baseline. And that baseline could be either all the data that they've ever recorded, or it could be a piece of time where they're sleeping to make sure that's the minimum stress level that they can record. And then we compare these values together and obtain a stress score from that. So we're currently testing this algorithm with over 200,000 data entries that we've collected over the last month. So here's an actual sample of a stress level chart that we've recorded. This was actually from this Tuesday that I personally recorded. So in an office environment like the one we've been working on, it's not really common for something stressful to happen. It's a very controlled environment. But as you can see, at some point in the chart, I almost dropped my cell phone. And you can kind of tell that my heart rate increased. And I kind of panicked as I tried to fumble and catch my phone. So this is good, though, because it shows that we actually are making progress on our stress algorithm, and we're able to detect at least some sort of excitement or stress. This is the heart rate signals for that period of time. And as you can see, there's a point where my heart rate increases rapidly as I try to catch my phone. And this is the galvanic skin response chart for the same event. So now that we know that we're somehow able to track the stress, or at least making progress towards that, we've determined that developing an application like this is feasible. We've been testing with 4 Microsoft bands in our office, and we've been discussing testing plans with nurse managers to see if we can actually implement this application in the field. So in the future, we are going to be using our data that we have, and we are also going to be collecting more data to improve our stress algorithm. But we have also determined that the galvanic skin response sensor on the Microsoft band is a bit unreliable at this time. This is because as you put on the band, over the next 15 or 20 minutes, moisture and sweat starts to accumulate under the band. And since the galvanic skin response is based on electric resistance of your skin, it causes the band to give you sort of erratic signals. So because of this, we might be considering using different devices in the future to improve our stress detection algorithm. So I'd just like to thank my mentor, Hyunhee Kim, and my collaborators, Ming Dai, who's sitting over here, Victoria No, who's up there, and Hyundai Kim for setting up our database. He's right over there. Also the device testers, Vincent Yao, Ming Dai, Jonathan Wicks, and Victoria No. We also received some advice on our application for certain features that we might want to have from Beverly Morris. And we also received advising from Claudio Farkas on certain devices that we might want to use. And finally, I would like to thank Dr. Ono Machado for helping to fund the devices and help purchase those, as well as all professors, staff, and interns, iDASH and DBMI, and the National Institute of Health. Thank you.
So her topic is improving mental wellness through expressive art therapy-based social support.
Good morning, everyone. I'm Elamon, and then my project is improving mental wellness through expressive arts therapy-based social support. This project started when I joined iDASH, so today I will talk about the early stage of it, which is the expressive arts therapy literature review. My mentor is Dr. Gina Hug. I'm an Elamon second-year master's student from University of Michigan, majoring in health informatics. So for this project, our objective is to combine expressive arts therapy and then social media together to help college students manage their mental wellness. Why this is important, I will break it down in the next few slides. Does anyone know what is expressive art therapy? Okay, nice. So expressive arts combine the visual arts, movement, drama, music, writing, and then other creative process to foster deep personal growth and then community development. And then the expressive art therapy is the application of expressive arts in a therapeutic relationship to support, maintain, and improve psychological, physical, cognitive, and then spiritual health of individuals of all ages. Speaking to visual arts, I'll give you some examples. So they are called color block, screen ball, life inventory, and lifeline. The goal of them is to initiate clients to make connections between their past experiences and the problem they have, and then further to help them find potential solutions. Another kind of expressive arts therapy called beauty spots. I exercise the beauty spots with my friends. And what is beauty spots? For example, Hannah. What I did with her is I asked her the beautiful spots or lovely things she had seen that day, and then asked her to draw or write on the paper so that we can solidify the beautiful memories in her life and then build a habit finding positive things in life. Does anyone recognize the icon in the middle? It is Pokemon Go, yes. Pokemon Go was released on the 7th of July to United States, and then it only took 13 hours to reach the top of the highest gossiping app chart in the United States. This app, we can see today, is reshaping the people's lifestyle in terms of the activities and the social activities. So this is the power of social media, and then that's also why we want to combine our expressive arts therapy with social media. Okay, so we are targeting college students, but why? Based on the research conducted by National Alliance on Mental Illness about mental health around college campuses, 1 in 4 students have a diagnosable mental illness, and then 40% do not seek help. 80% feel overwhelmed by their responsibilities, and half has been so anxious they struggled in school. So now we know expressive arts therapy can help with mental wellness, and then we know social media can offer us that powerful influence. And then we also have our target population. And this is how we're gonna get there. So we have been regularly meeting with Expressive Arts Institute and the CAPS of UCSD, which is the counseling and then psychological services. We talked about and we defined the points of intervention and the agenda of our study process. In collaboration with them, we will develop a easily online support group for in which UCSD students can exchange support and get services. Okay, let's move to expressive art therapy literature review. So here is the queries in terms of the keywords combination we have so far. And basically, we come up with our keywords around expressive art therapy and then college counseling. And then we combine them together, search them through search engines, and we got results. And then we analyze our results to refine our queries. So here you can see we ran 14 queries through Google Scholar, PubMed, JSTOR, and ACM. I'll walk through how we get our results. Okay, so we ran 14 queries through search engines, and we got 6875 records identified. And then we defined our inclusion and exclusion criteria. We include any kinds of expressive art therapy beyond just visual arts. And then we include expressive art therapy in which it has to be used among young people because we target college students. We exclude those syntheses and then books, and then those not written in English, and then those in which expressive art therapy is not used as an intervention. Also, we defined our search strategy. So basically, we search through search engines, and then we look through the title and the abstracts. We keep finding relevant results until non-relevant results shown. And then we got 5020 records screened as a result, and then 256 records meet the inclusion and the exclusion criteria. Oops. Okay. Then we remove 23 duplicates, and then finally we got 233 records for qualitative synthesis. This image shows us it's by looking at visually how our results getting from different queries, and then later on we will remap this board based on the variables we need in terms of like outcomes and then intervention and then results. So far we examined 14 articles, and then for each of them we document the paper, country, intervention period, study design, sample, outcome measured, and results. So far from the 14 records, we analyzed them, and then we got this result. So basically, over 90% of the study conducted in United States, and then they last 2 to 20 weeks. For each therapy session, it takes half to 3 hours, and the sample size varies from 1 to 93. Half of the study is single group study, and half of them with control group. So for the outcome, over 80% have significant difference, which means the expressive arts therapy actually improved the client's performance. All right, so in the early June, we submitted a IRB application, and then we just got their revision request for group, focus group interview, and then we got a approval for access to get CAPS data. So the CAPS data is a questionnaire so students come to CAPS and then get their help, so they fill up the questionnaires. So far, we get the past 3 years questionnaires, and then we will analyze them. And then we will use the results from literature review to give us a better science on what kind of expressive art therapy works for what kind of people, and then use what kind of measurement to get what kind of results. So then after we get approval from ARB, and then we will design our focus group and then conduct focus group interviews to get students' needs around social media and then their barriers to get help. Then we will create a persona to get our online support group design, and then conduct usability tests with users to get their feedbacks and then refine our design. Finally, improvement online support group. So for this internship, my focus is the literature review, and then I will continue working with Dr. Huck after I came back to University of Michigan. And we believe our online support group will meet students' needs and lower the barrier for them to seek help, and then prevent incidents due to lack of efficient assistance. So here I would like to thank my mentor, Dr. Jana Huck, and then our all collaborators, Dr. Henny Kim, and then the UCSD CAPS and the Expressive Arts Institute, and all professors, staff, and interns at iDASH, DBMI, and NIH. Thanks.
And her topic is committed, complementary integrated therapy evidence detector.
Hello, and thank you for coming. My name is Hannah King, and the project I've been working on this summer is called COMMITTED. It stands for Complementary Integrative Therapy Evidence Detector. The mentor for this project was Dr. Hyun-Hee Kim, and a little bit about me. I am studying biomedical engineering at Vanderbilt University. Today I'll be talking about the background of our project, the project flow and methods, results, and future directions. So first, what is KIT? KIT stands for Complementary Integrative Therapy, and the NIH, or the National Institutes of Health, defines KIT as a group of diverse medical and healthcare systems, practices, and products that are not presently considered to be part of conventional medicine. It was previously referred to as complementary alternative medicine. However, the term alternative inferred that the therapies in place were in place of conventional medicine as opposed to integrative. KIT therapies include alternative medical practices like acupuncture, mind-body interventions like yoga, biologically based systems like herbalism, manipulative methods like massage therapy, and energy therapies like Reiki. In this project, we decided to narrow the scope of our study to KIT for cancer pain. Chronic symptoms in cancer patients have an adverse effect on their everyday life. It can lead to physical limitations and decreased health-related quality of life. Many patients dealing with these debilitating symptoms turn to KIT to help cope with their disease or treatment-related symptoms like pain, fatigue, mood disorders, and sleep disturbances. KIT is widely used even outside the cancer population, as 75% of U.S. adults have used at least one KIT in their lifetime. This is according to the 2007 National Health Interview Survey. However, most patients are not well informed of the benefits, effectiveness, or possible side effects that KIT may have on their specific conditions. Although patients are very interested in having information on KIT, most patients report friends, family, and media as their primary source of KIT information. In addition, as all patients and cases are different, KIT effects will also be different depending on the case, but usually the information that's available to them is very general. While an estimated 64% of cancer patients use KIT, 77% of them do not share this information with their doctors. And this can become a problem as complementary therapies are both, they can both aid and interfere with medical treatments. For an example, some studies have shown that garlic, herbs, and high doses of antioxidants may interfere with the effectiveness of cancer treatments. So our goal in this project was to create a consumer-oriented information resource that provides published studies on KIT, allowing users to personalize their search, helping patients realize the importance of carefully selecting KIT, and encouraging discussion of KIT use with healthcare providers. So this is a quick overview of what our project flow was. We started off with acquiring a corpus of PubMed articles that were published within the last 10 years, using queries refined to just KIT for cancer pain. Then we began the reading and annotating process where we analyzed sentence patterns. After determining the metadata list, we used two methods to extract metadata. First, manually reviewing, and second, utilizing an algorithm. With more development and a larger article corpus, we hope to build an algorithm that reaches all the other metadatas. A software that we used for the annotation process is called eHost Annotator, and you could assign words or phrases to classes. So this is a list of the metadata items that we decided on. It was constructed after reading the corpus of articles. The list is composed of entities like target age, symptom, and KIT effectiveness. All that could be used as useful search elements, sorting categories, and important information that the patient may want to know. And this is a portion of what our metadata table looks like. The rows are organized by article, and columns were filled with metadata. Values were standardized and normalized when possible. While a meta table like this can give users a quick summary of evidence provided in articles, review and abstraction of this data takes a long time and requires readers to understand the content of the article and results. Most comparable KIT information resources use healthcare providers or other therapy experts to manually update summaries and populate databases. If an algorithm could be developed that could automatically pull this metadata from papers, it would be significant improvement in faster and easier abstraction of usable metadata. So we decided to start by locating the metadata KIT type and target symptom within the text. We utilized the UMLS meta thesaurus. We constructed a dictionary of all the possible KIT therapies identified in the system. The meta thesaurus is a vocabulary database that contains information, various names, and just relationships between biomedical and health-related concepts. Our current KIT list has around 200 KIT types, ranging from common therapies like acupuncture to less common therapies like crystal healing. Target symptoms were captured using the NLM MetaMap. MetaMap is a medical text indexing tool that uses natural language processing to map terms to the UMLS meta thesaurus. The interactive version of MetaMap that we use allows you to restrict the semantic type that is returned. After testing with several articles, we decided that the semantic type sign or symptom and mental or behavioral dysfunction captured most of our desired symptoms. So we restricted the semantic type to these two and then got the rest with a small dictionary of symptoms that we acquired from reviewing which symptoms were added or missed in the list. A Python script was used to format the results in an organized table. This is what our algorithm results look like. As you can see, there is a column for title of the article, sentences within the article that have at least one KIT type in the sentence, and then the KIT type found within the sentence, and then MetaMap findings that map to QEs and their semantic types, symptoms that are a dictionary that found that MetaMap might have missed, and the last two columns are used to review whether there were added or missing symptoms. As for the front end of our application, users will be able to input their symptom, their kit type, age, gender, and or medical diagnosis. As for the functionality specifications, articles will be sorted first based on best match, second article evidence strength, and eventually third crowd response. Search results column would have customizable sorting options where users can choose which columns they wish to see and also by which categories they want to sort the table by. We also plan on giving users the option of saving and downloading their search results and giving them a link to the full text. So this is what our home search page looks like. Users can input their information into the boxes and leave however many fields they wish blank. Press search and this search results page should appear. Search results will be listed in order of best match, then strength of evidence, and when we implement crowd response, user ratings. But these sorting and viewing options can be customized by the user. Results are listed by article and the table can be saved or downloaded. So in this proof of concept study, we developed Committed by manually extracting metadata from published papers and building an algorithm in order to provide evidence for published kit studies, equip users with personalized information, promote cautious use of kit, and encourage discussion with healthcare providers. However, there is a lot more work to be done. Committed has much potential to become a powerful tool and a helpful tool for patients dealing with burdensome symptoms. Future directions would be to expand the algorithm to reach all the other metadata, and the short time period of my internship limited our algorithm development to just kit type and target symptom. We would also like to adhere to scoring standards that are already in place, such as the Cochrane recommended grade. This standard is for the scoring of the quality of evidence and strength of recommendations. The application could also serve a wider audience beyond cancer patients and their symptoms. And as it can be difficult for patients to understand the metadata table results, we would like to provide a more patient-friendly summary and visual audio aids that would significantly improve the patient's education. Our application can point users to an existing online communication and support groups, and we also plan to incorporate crowd response for user ratings and paper abstractions. We look forward to working with UCSD's Center for Integrative Medicine at Moores Cancer Center to test Committed and improve patient-friendly use. Finally, I would like to thank my mentor, Dr. Hyunhee Kim, collaborators Vincent Yao, Alex Richardson, and Victoria No, all professors, staff, and interns, Lori Johnson from the Center for Integrative Medicine at Moores Cancer Center, iDASH and DBMI, and NIH. Thank you so much.
Hi everyone, my name is Sanjay Ravi Shankar, and I'm a fourth-year undergraduate student in the Bioengineering Bioinformatics program here at UCSD. And today I'm here to talk about my project this summer, which was the contribution of rare germline variants to cancer susceptibility using PCOG data. And PCOG is a pan-cancer analysis of whole genomes, and so that's another project that we were working with. And so along with myself on this project team is my mentor, Dr. Olivier Harris-Mendy. So a little bit of background. So common variants, or GWAS is used to study mostly common variants and genotype-phenotype interactions with cancer. But these common variants have a very small effect size, as you can see in the bottom right-hand corner of this diagram. And because they have a very small effect size, these variants show very very heritability to cancer. So we'd rather study the very rare variants, which have a minor allele frequency less than 5%, in order to kind of bridge that gap between the heritability of cancer. And so rare variants are not identified by GWAS and have a much larger effect size, as you can see here. And they are valuable to study because they could explain this much larger percentage of the heritability of cancer. However, there are very limited studies involving rare variants since they're very hard to find and require a lot of money to whole genome sequence the data set. The statistics are also very hard to calculate since you need to aggregate the statistics since they're so small and so uncommon. And so the question remains, where should we look for these rare variants? And so the answer lies in cancer predisposition genes. And so these are genes which confer moderately or highly increased risks in cancer. There are 114 cancer genes that have been discovered. And on this diagram here, proto-oncogenes are shown in red, and tumor suppressor genes are shown in black. And so these genes are perfect candidates for studying information regarding rare variants because most functional variants have the highest likelihood of being in regulatory regions surrounding these cancer genes. So the cancer data that we will be using is provided by the Cancer Genome Atlas and the International Cancer Genome Consortium. And so this is public data, part of the PCOG project. So there are 2,800 whole genome sequence samples, and the coverage is about 30x, which is good coverage for performing association tests. The variants have been uniformly called and genotyped using the GATK haplotype caller. And so this is important for analyzing rare variants as a group and an aggregate rather than individually, as you would normally do with GWAS. And so in our data set, we also have 40 different cancer types. And so here we have a distribution of the different cancer types, the 40 different cancer types. So on the left-hand side, as you see, we have the farthest left is the highest frequency, and that is liver cancer, followed by pediatric brain cancer. And so these are the cancers that our patients have shown. And so here we have the phenotypic data. So here we have first a distribution of the age of diagnosis of the patients. And as you can see, a majority of the patients were diagnosed with cancer between the ages of 60 and 80. And so we also have a patient count of 1,367 male patients and 1,093 female patients. And as with most data sets, we have missing values. So we have 406 missing values for age of diagnosis, 327 missing values for gender, but we have no missing values for cancer type. And the main phenotype that we'll be studying here is age of diagnosis. So our main project objective is to study the effects of rare germline variants on cancer susceptibility among the different cancer phenotypes. And previous studies have analyzed the effects of germline variants on cancer type and coding regions, but our main focus is the non-coding regions, so specifically the regulatory elements surrounding cancer genes and GWAS SNPs. Previous studies usually have a controlled data set as well. Since we don't have a controlled data set, we prefer to use age at diagnosis as a continuous phenotypic variable that will act as like a regression line. And so our main hypothesis is the higher the number of rare variants in a particular region, the earlier the age of diagnosis. And so here we have the tools that we are using for the project. So first off is variant tools, which is a variant database tool. And this is what we use to perform queries on all the variants that we've imported into the project. And so this tool is useful because we need to interrogate specifically the non-coding regions where rare variants are likely to be functional around cancer gene regions and around GWAS SNP regions. So this database allows us to essentially query that we can sort based on region, minor allele frequency, which I'll get into a little later on, yeah, et cetera. So we also have variant association tools, and these are the tools that we will be using to perform association tests on the variants and the phenotypes. So the two main methods that we will be using to perform these association analysis is the variable thresholds method and the SCAT-O method. So this is the data analysis pipeline that we have right now. So we import the variants from a VCF file format. We annotate the variants with dbSNP and exac. Then we annotate the variants using the ANNOVAR gene-based annotation, that pipeline that is actually built into variant tools. And then we're going to add the roadmap enhancers database, which actually contains the information about the regulatory elements, the enhancer regions on the chromosomes and tissues. Then we're going to import the phenotypes into the project. We're going to calculate genetic burden over each interval and then perform rare variant association tests. So I spoke about genetic burden in the previous slide, and genetic burden is typically defined as a genetic debt due to a harmful mutation, but that doesn't really help in our context. So we refined that definition to be an aggregate count of all the rare variants over a particular region interval. And there are different extents to which each variant can be harmful. And so to quantify this, we have an algorithm to predict functional consequence of variants. And we can sum these quantities to get a test statistic over each region that we're looking at. And so I spoke about the methods that we were using to perform these association tests. And the first one is variable thresholds, which varies minor allele frequency thresholds and tests genotype-phenotype association. And so the final association test using the variable thresholds method shows the minor allele frequency threshold at which the association is strongest. And so this method essentially acts as a control to make sure that we are making associations with rare variants and not any like common variants. And with the SCAT-O method, that's a region-level association test. So it aggregates SNP test statistics and computes a p-value over each region that we are looking at. And so here we have sort of depictions of the association tests over which regions. So we're going to be looking at cancer gene regions and GWAS SNP regions. So the first diagram shows cancer genes most susceptible to lung cancer and ovarian cancer. So lung cancer being on the left and ovarian cancer being on the right. And the higher the bar on the diagrams is the lower the type 1 error, which is measured by false discovery rate. And the second diagram is a depiction of how a subset of rare variants in a specific region can influence a phenotype. And so this is taken from another study where they did a case control analysis. But as I said before, we don't have a controlled data set. We're using age of diagnosis as a continuous phenotypic variable that can correct for cancer type differences and gender differences. So current progress right now is we're currently running the data analysis pipeline on a similar test data set. So the TCGA and ICGC are providing us with an updated data set. So once we finish running the pipeline on this test data set, we can kind of scale up to accommodate this much larger data set. And so getting to this point took some time. I needed to become familiar with variant tools and all of its capabilities as a database query tool. So I needed to be able to make those queries and basically ask anything of it and then get results that I wanted. So I started with a small size of the data set to train on. And then I had to prepare a phenotypes file from the ICGC and TCGA data to get the phenotypes that I wanted, which were age of diagnosis, cancer type, and gender. And then scaling up the project is the most challenging part because the data set is very large, so it requires a lot of computing power. So if our hypothesis is true, and then there is an association between rare variant count and age at diagnosis, this would greatly further our understanding of cancer susceptibility. And so this would improve our model of genetic risk in cancer prevention, and the missing heritability would be accounted for, and we can predict genetic risk at a greater rate. So I'd like to thank my mentor, Dr. Olivier Harris-Mendy, the collaborators, TCGA, ICGC, and PCOG, all the professors, staff, interns, iDASH, and DBMI, NIH, and the CTRI iDASH team. Thank you.